Hello, welcome to Physics 2, Lecture 25.2, Electromotive Force. We're going to begin this discussion, or actually use this for the whole discussion, but we're going to begin by considering a conductor of length L, which you can see on the image on the right. Our conductor is this rectangular piece of material that moves with a velocity v, as you can see to the right, in a uniform magnetic field given by B, in this case, a bunch of X's pointing into the page. So we're simplifying this by assuming that the motion is perpendicular to the magnetic field. So the motion is to the right, the magnetic field is into and out of the screen. As a result, those are perpendicular. So let's take a look at what happens. We have a conductor. Inside of that conductor is a bunch of charge carriers, or charges. If the conductor is moving to the right with a velocity v, well, so must be all of the charges inside. So every individual charge inside is also moving to the right. Well, remember from our past lectures that a charge moving through a magnetic field will experience a force. That force is given by the equation QVB sine alpha, but since these are perpendicular, we have removed the sine alpha term to leave us with QVB. We should know, by the right-hand rule, if our motion is to the right, so our thumb points to the right, our magnetic field is into the page, so our index finger points into the page, our middle finger should point upward. So positive charges are forced upward in this conductor as a result. So we will see them migrate toward the top end of this conductor. Well, if that happens, what about the negative charges? Well, that will leave an excess of negative charge at the bottom of the conductor. And as a result, by definition, we have just separated charge. The positive charges are forced toward the top, negative charges are left behind at the bottom. As a result, we now have charge separation. If you recall our material from the beginning of the course, when we talked about electric fields and electric potential, we discussed how potential was created. Electric potential, or potential difference, in other words, voltage, is created anytime charge is separated. And as a result of that, it produces an electric field. So we now have separated charge, plus on top, minus on bottom, and an electric field pointing, as we know, from plus to minus. So as a result, though, something interesting happens. We're trying to get the magnetic field is trying to push the positives up. But now we have an electric field that wants to move the positives down, right? Positive charges want to move with an electric field. So it's actually starting to oppose this motion. So we actually start to get what is basically a battle between these two forces, the force of the magnetic field on the charges, and now the force of the electric field as well. So we get a remarkable result. This will continue only until those two forces have balanced. In other words, until we've separated enough charge so that there's a strong enough electric field now to resist the motion from the magnetic field. So you have the force of the magnetic field, the force of the electric field. The electric field force keeps getting bigger and bigger until these two come into balance. In other words, we can set those two forces equal to one another. The electric field force was given by Q times E, and the force of a magnetic field is QVB. So we're setting those two terms equal to one another. Well, when this balance happens, we see that there is no longer a net force on the charges. They're balanced. And so they don't move anymore, and thus we reach what we call equilibrium. Right? No net force, nothing's there to push them around anymore, and so they are in equilibrium. Looking at the equation above, if we cancel out the q's on each side, we're left with an expression for the electric field in this state. The electric field at equilibrium is given by V times B, where again, V is the motion of the charges, the velocity, and B is the strength of the magnetic field. Now, remember that we have a potential difference as well between these two ends of the conductor. It's almost, you can almost sort of think of this as a battery in a way. You have a positive end and a negative end. It's kind of like a battery. So we have a potential difference between these two ends. So if we wanted to solve for what that potential difference would be, we can use a previous equation that we had in our earlier material. We said that the potential difference is related to the electric field in the expression delta V is equal to E times L. So if we go back real quick, all we have to do is multiply this equation by L, and we now have an expression for the potential difference between the two ends of the conductor. Delta V equals VLB. Again, where V is the velocity, L is the length, and B is the strength of the magnetic field. So, to conclude this new material at least, we're going to basically add in one more technicality. Right now we're saying delta V, the potential difference, is equal to those three terms. But we do give this a special name, and it's been at the top of all these slides this whole time. First of all, let's go back to our discussion of a battery, because remember, I said that this situation is sort of like that of a battery. A battery, as we know, uses what we called a charge escalator to separate positive and negative charges. We thought of it as charges being lifted up inside the battery to a higher potential. We refer to a battery where charges are separated by these chemical means, using chemical potential energy, as what we call a source of chemical EMF. EMF is what we call electromotive force. So a battery does it using chemical means. But what we just learned about was using magnetic force to do it. And in order to produce that potential difference, in other words, an EMF, it's due to the motion of the conductor. If this conductor wasn't moving at all, we wouldn't see this happen at all. So it's due to motion, and thus we define this particular potential difference that's being created as a motional EMF, or electromotive force, which is given by the symbol epsilon, capital epsilon. And so we can write this as, instead of delta V equals VLB, we're going to write it as epsilon equals VLB. Now, this is typically an initial point of confusion for a lot of students. This equation is exactly the same as the one we looked at on this slide. We're just giving it a new name. Instead of potential difference, we're calling it EMF, or electromotive force. And note, force is a little bit deceptive because there's not an actual interacting bodies with a force between the two of them. The way I think about it is we are forcing charges to move. So it's kind of almost like water pressure instead. But anyway, the point is this is potential difference. It's just that it happens to be the potential difference created by a situation where you have a moving conductor. And again, it is the same thing, which means it is also measured in volts. So just be careful. Anytime you hear electromotive force, don't freak out. It's just potential difference for a specific scenario. So before we get into our quick checks and an example, I figured I'd just throw in one pretty neat application of this. So it is believed that hammerhead sharks are able to navigate using the Earth's magnetic field. It's likely that they can detect the magnetic field using their electric sense, detecting that field by sensing the motional EMF as they move through the water. So they have an interesting shape to their heads. It's, roughly rectangular in a long sense there, so you could think of this as being our conductor that is moving through a magnetic field, just like we saw here. Just pretend this is the head of a hammerhead shark. So here they are moving as a conductor through a magnetic field of the Earth, and we have the same situation. So the width of their oddly shaped head is an asset because they can use that to have a difference in potential between the two ends that is proportional to its length. So technically, the longer their head is, the more efficient they would be able to detect a magnetic field. So just kind of a cool result and a nice break from the details of physics. So let's conclude this lecture with some quick checks and then an example. Get ready for some more right-hand rule applications. This quick check asks, or says, a metal bar moves through a magnetic field. The induced charges on the bar are given by what? So think of your right-hand rules, how charges would be separated. Which of these options below is the correct response? Okay, well, I started out with a trick question. The answer is E. We are moving parallel to the magnetic field. If you move parallel to the magnetic field, remember that there is no force as a result of that. So there's nothing forcing the charges around because of this particular motion, and as a result, there's no separation of charge. So we don't see anything really happen to our charges. They just continue in their normal state. So again, just a trick question. The magnetic field and velocity are parallel, and so there's no force. So let's do another one where it's not necessarily a trick question. A metal bar, again, moves through the magnetic field shown, so the magnetic field is different this time. The induced charges on the bar are what? Okay, so in this case, again, apply your right-hand rule. You should get B as your answer. Our velocity points downwards, so our thumb should be pointing down. B is out of the page, so back toward you, which means your middle finger is going to point to the left, forcing the positive charges to the left, negatives to the right. So we have a left and right split between our positive and negative charges, with positives on the left, as shown in option B. All right, so let's conclude with one example, a very simple example, but just a really cool application of it, especially since I do tend to have a lot of aviation students. A plane is basically a conductor, and the Earth has a magnetic field, so planes flying through Earth's magnetic field are a perfect example of everything we've just discussed. So in this example, a Boeing 747 aircraft with a wingspan of 65 meters is cruising at 260 meters per second over northern Canada, where the magnetic field of the Earth of 5 times 10 to the minus 5 Tesla is directed straight down. The question asks, what is the potential difference between the tips of the wings? So the very first thing I'm going to do is draw a picture of what we're looking at. A very basic one. I'll draw this off on the side here so I have room to write. So I'm going to draw a simplified view. Let's just say our plane is a rectangle like we've been discussing. We have a magnetic field, we're told, as pointing, I'm going to have to use different colors here. The magnetic field is pointing straight down. So let's say this is a top-down view. So we should have a magnetic field then pointing into the page. So everywhere around this plane, if we're thinking a top-down view, we have a magnetic field pointing into the page. So I'm using X's to indicate that. And let's assume that our plane is moving to the right, just like in the examples we've been doing. Okay, so there is that. And our magnetic field, again, oops. Let me fix this here. Okay, hold on one second. Sorry, my screen got all messed up here. Okay, and so our magnetic field, again, is pointing into the page. I'll make sure to label that as green. So if this is the case, we're setting this up to mimic what we saw in our demonstration in the beginning of the lecture. We have a conductor moving to the right, magnetic field into the page by the right-hand rule. That means we should get a force pointing upward. So our positive charges are accumulating at the top, and our negative charges, this might not show up very well, are accumulating, oh it does, at the bottom. So we're looking for the potential difference between the tips of the plane wings. In other words, we're looking for the plane's motional EMF, epsilon. This is potential difference for a moving conductor. Oh, my dog is playing with toys. Hold on, sorry. Hey, no, not right now. Okay, we might have to deal with this. So our equation for motional EMF is VLB. Luckily, since this is a pretty basic problem, we actually do know all of these terms already. We know how fast the plane is moving, we know how long the wings of the plane are, and we know the magnetic field strength in the background. Chaser, no. I'm going to have to keep taking toys away from him. I forgot to put them away for this lecture. Anyway, so the speed of the plane is 260 meters per second. We know the wingspan of the plane is 65 meters, and the strength of the magnetic field is 5 times 10 to the minus 5 Teslas. So if we plug this into our calculators, we will come up with an answer of roughly 0. If I can read my own handwriting, 85 Teslas. Or not Tesla, volts. 0.85 volts as our answer. It's volts because this, again, is a potential difference. So, very basic example to get us started with this material before we jump into it a little bit further in our next lecture. So, as always, thanks for watching and have a great day.